Let's take a look at the Euler and the Hamilton paths. So first we have the Euler circuit. The Euler circuit traverses every edge of G and then arrives at the initial vertex. We have the Euler path, where you can traverse all the vertices of the graph and then arrive on the same by going through the edges only once, all the edges of the graph only once. Then we have a theorem here. We say that a connected multigraph, so remember a multigraph means that you have more than one edge between two vertices. Okay? So if you have at least two vertices in a multigraph, you know that it has an Euler circuit if and only if each of the vertices has an even degree. Okay? Another theorem is that a connected multigraph has an Euler path, but not an Euler circuit, if and only if it has exactly two vertices of odd degree. During the synchronous, we'll draw some graphs and we'll realize that this is actually true. Now, let's take a look at the Hamiltonian and paths and circuits. First, we have the Hamiltonian path. So the Hamiltonian path goes through every vertex of the graph. And the Hamiltonian circuit goes through every vertex of the graph, and it arrives back at the original vertex. And exactly once. So it passes through these vertices exactly once. Now, how difficult is it to determine whether a graph has a Hamiltonian circuit? It's very difficult. And again, that's another fundamental problem in computational complexity theory.